Okay, well, this is our third meeting of the Lyme project. And the focus of this whole meeting was to kind of cover the buffer pH methods. And an addendum to that is that John Spargo and Sarah Lyons is going to give a brief overview of what they've got for the survey information from the pH and buffer pH surveys they did with the land-grant university laboratories. So without further ado, to keep stuff on schedule, Frank, you want to go ahead and do a quick introduction yourself and go into your presentation?
Sure. Yeah, my name is Frank Sikora. I'm at the University of Kentucky. I'm Director of Laboratories at the Division of Regulatory Services we have here. I was in charge of just the soil testing lab up to 2012. I started here in I started here in 1998. In charge of the lab from 98 to 2012. My new role includes not only the soils lab, but the other labs, fertilizer, feed, seed, and milk. So that's the introduction on myself. I will share my screen here. And Bob asked me to give a presentation on the buffers I helped develop. And I put together about a 30-minute presentation. Hopefully I'll get through it a little less time, hopefully, so we can have some time for discussion. But I'll just start off with this title slide here. You all see the title slide in full? Yeah, okay. Okay, so what I'm going to be covering here are introduction to soil buffer chemistry, developing the Sikora and more Sikora buffers, and developing the Sikora 2 buffer. I also want to thank Amber Moore and Carl Makepeace at Oregon State University, because they conducted some recent studies just in the last couple of years that really added some more information to the Sikora 2 buffer that I'll discuss a little later. Well, when I first started into trying to understand buffers and study the topic, one graph that I thought was really important to understand it was found in Shoemaker's dissertation. And Shoemaker is the S in SMP buffer. You don't find this graph very much in literature, but I found it in his thesis. And it's just this complicated graph here. And I'm going to talk about some of these lines later, but what I want to focus on now is just this line right here, which represents the titration of just the buffer. No soil, just the buffer and water in a beaker, and you add acid to it. You're going to start off at some initial pH of the buffer, and with increased amount of acid, the pH would decrease. So you're looking at the titration curve of just the buffer. This is a graph of several buffers that are out there with respect to that titration curve of adding acid to the buffer. Buffer and water is mixed together in the volume of water and buffer is the volumes that are used in the method of testing first soil pH with water and then adding a certain volume of buffer. So you have that certain combination of buffer water, you add acid, and you're going to get a decrease in pH. So you see all these buffers we have out there, they have all different buffering capacities with respect to the pH with addition of acid. The Adams-Evans buffer is in orange here, and that's AE. And that is a really strong buffer. When you add acid, the pH does not decrease that much. The pH begins at 8 and it decreases moderately with increased acid. The SMP buffer is a weaker buffer. The pH decreases more drastically with increase in acid. The Adams-Evans, I'm sure everybody's aware, is used on altisols, low CEC soils. It was developed in Alabama. The SMP buffer was developed in Ohio on higher CEC soils, such as observed in alpha soils. You often hear in the literature that the buffer chemistry is well suited to a particular type of soil. I don't believe that to be the case. I think these different buffers are appropriate for different types of soils because they're calibrated. The buffer pH was calibrated to lime recommendations for those particular set of soils. So that's it on the introduction of the chemistry. In creating the Sikora buffer, the objective was to create a buffer to result in the same soil buffer pH as SMP buffer. And the main reason for that was to get rid of the hazardous chemicals, paranitrophenol and chromate in the SMP buffer. These are chemicals that should not be dumped down the sink. They had to be disposed of a certain way. So not only myself, but others have been looking at these buffers to remove these hazardous chemicals. One aspect of all these buffers that I showed earlier is they have all combination of different acids and bases in the buffer. And this combination of these different acids and bases results in the linear decrease in pH as you add acid. That is very important for all these buffers. You have to have linearity, a linear decrease in pH with the addition of acid. So with this work, we wanted to get rid of paranitrophenol and chromate, and it was replaced with the chemical abbreviated as MES and imidazole, and you see the pKa's there. I just played around with a lot of calculations, theoretical calculations to determine what concentrations of these chemicals would be appropriate to result in a linear decrease that was exactly the same as the SMP buffer. So again, I didn't work with any soil at all in this project. It was just looking at a solution of water and buffer, adding acid to it. You have a decrease in the pH with the addition of acid to the SMP buffer. Creating the Sikora buffer, I mimicked that with the same titration curve with those replacement chemicals. Well, this graph shows a comparison of using the Sikora buffer with comparing the Sikora buffer pH with the SMP buffer pH. Adding 10 mils of buffer to 10 cubic centimeters of soil, and then adding 10 mils of the buffer, either Sikora or SMP buffer. There was a good agreement between the two. The one-to-one line is here, and you see the scattered points around the one-to-one line and a high R squared. This is a photograph of the Sikora buffer on the left and the SMP buffer on the right. When I show this slide, I like to tell people I was really proud to create a buffer that did not look like piss. The SMP buffer just looks toxic. It looks nasty. The Sikora buffer looks clean and fresh. The publication on creating the Sikora buffer is shown here, if anybody wanted a reference to that. Well, when I presented this at the Series 6 meetings, Kathy Moore at Clemson, she said, well, can we do the same thing with Adams-Evans? Adams-Evans has paranitrophenol in it. Could we replace that with another chemical to have the same acid titration and result in the same buffer pH? So I said, yeah, we'll try it. And we worked on that. We got rid of paranitrophenol in the Adams-Evans buffer. We replaced that with MES and MOPS. With this buffer, we had such a mess, we needed MOPS. See, I mean, that was a joke there, guys. So, okay. But the combination of these different acids was played around with to make sure that we had a linear decrease in the pH with increased acid. This is the titration curve of the Adams-Evans buffer. And this is the titration curve of the Moore Sikora buffer. So we just had the same titration with respect to adding acid. The reference to that work is shown here. So the work I showed so far was pretty much the chemistry project, the laboratory project. It didn't really evaluate or look at Lyme recommendations. The objective was just to create a buffer that would give the same buffer pH value as the buffers that were being replaced. The Sikora 2 buffer looked at it a little bit more with respect to the Lyme recommendation that we would make based on the buffer results. And the objective of this work was to develop a buffer and a method to determine the soil's pH buffer capacity, which can be used to make Lyme recommendations. So the soil's pH buffer capacity are the important words here in this objective. And this is a graph from Shoemaker's thesis. It's just showing typical Lyme response curves with the addition of calcium carbonate to soil. We're all familiar with this. You increase calcium carbonate, you're going to get an increase in pH for soils that are very acid. With these Lyme response curves in developing a method, it's very important to know what the slope is. That's the important parameter I think we should seek to make Lyme recommendations. And this was the objective not only in the work for the Sikora 2 buffer, but also the work that David Kissel did with the single addition calcium hydroxide method in Georgia. The objective was to determine what the slope is for the Lyme response curve. Because between a pH of about 5.2 to 7.2, it's pretty linear. So if you determine the slope of the response in this pH range, it has a lot of advantages. You can determine a Lyme requirement to any pH. You don't need separate tables or equations for different pH targets. You could use algebra to calculate what Lyme is needed to reach a certain pH. And it's also a method would be suitable across widely different soil types, low CEC to high CEC soils. And you could also possibly use it to predict how much acid to add to decrease pH. So there's a lot of power, I think, in knowing what the slope is for the Lyme response curves. Now, it's difficult if you have soils that are very acid because you have aluminum buffering the pH. And if soils are very high in pH, you have calcium carbonate buffering the pH. So knowing the slope is only going to be instructive between pH 5.2 and 7.2. This is a typical calibration table for SMP buffer, showing how much Lyme to recommend at different target pHs with respect to what the soil buffer pH is. So for one target pH, it's only looking at what the soil buffer pH is to make a recommendation on how much Lyme to add. When I came to Kentucky in 1998 and I looked at our Lyme recommendation table, I saw that they were using the SMP buffer and the water pH of the sample together to make a Lyme recommendation. And I'm showing just one of those tables here. The previous slide showed a table for each target pH. I'm showing here the table just for the target pH of 6.4. And, I asked, well, why are you straying from the initial SMP calibration tables? And they did not have any, the soil specialists didn't have, all they had was empirical data, a best guess at what these recommendations should be. And their argument made sense. If you had a buffer pH of 6.5 and you looked at just the previous recommendation table looking at just buffer pH, you might have a recommendation of 3 tons per acre. But if you're starting off with a pH that is really low, it would make sense that you should apply more lime. And if your pH is higher with the same buffer pH of 6.5, you should have less lime being applied. So that made sense from an intuitive point of view. My goal was to develop an equation that could predict this, that could use a lime response curve that could be evaluated from buffer pH to predict these values we had in our recommendation table. So to do that, I went back to thinking about this titration curve of the buffer with addition of acid. And you have a certain soil buffer pH that you might get from adding the buffer to the soil. And here it's a soil buffer pH of 6.5. So it would take so much acid to decrease the pH of the buffer from 7.5 to 6.5. You could also overlay on this graph the amount of alkalinity from the buffer that is required to increase the soil pH from some initial pH, here about 5.2, to this soil buffer pH of 6.5. So this red line is a lime response curve. It's the pH of the soil increasing with respect to with the addition of the alkalinity from the buffer. So if you take that concept from the previous calibration table that if you're in the middle of a soil pH, you're going to recommend so much lime to get to a target pH value. But if the pH is higher, you would require less lime to get to that target pH. But if the pH is lower, you would require more lime to get to that target pH. So, this is just graphically trying to make sense of what was in the table. That the lime recommendation should not only be based on the soil buffer pH, but it should also be based on the initial soil pH. And this concept of using 2 pH values to determine what that lime response curve is what was used in the double buffer method that Juan developed in 1974. I just show this here to indicate that it wasn't a new technique that I was using on using 2 pHs, because the double buffer methods also use that same concept. The difference I was interjecting in the study was having one of those pH measurements just being the initial soil pH, not a pH from a second buffer. So we go back to this curve here where we have a lime response curve of the initial pH and then the soil buffer pH. And I showed just a general graph of that a couple slides ago, but when you start thinking about what the salt concentration is with an initial soil water pH and the soil buffer pH, I started to realize that I was comparing apples with oranges, because the soil buffer pH has a salt concentration of 1 molar potassium chloride. Soil water pH, it might be 0.01 molar ionic strength. So that's why I introduced the 1 molar potassium chloride soil pH, to get the ionic strength of that initial soil pH to be the same as the ionic strength in the soil buffer pH. so that apples could be compared with apples and a adequate line response curve could be drawn between those 2 points. The target pH, if we're looking at this line response curve, the target pH would need to be what the pH is to raise it, what lime is needed to raise the pH to a 1 molar potassium chloride soil pH for target. And the working with all this, you have to get what the relationship is between your soil water pH and 1 molar potassium chloride soil pH. It's approximately 1, so that's why you see this decrease in 1 pH unit. And this target pH unit of 5.4 is approximately equivalent to 6.4 for a soil water pH. So the figures on the right are showing what the difference is between a Sikora buffer and a Sikora 2 buffer. In the Sikora buffer, you see the salt concentration in this buffer, as it was in the SMP buffer, is 2 molar potassium chloride. And that high salt is in there to exchange, to release exchangeable acidity in aluminum from the soil so it could be neutralized by the bases in the buffer. So when you're adding 10 mils of 2 molar potassium chloride solution to 10 mils of water, the final ionic strength of that solution is 1 molar. Well, if we're going to start off with a 1 molar potassium chloride soil pH as the initial pH, the concentration of potassium chloride had to be reduced in the buffer. So that's what the Sikora 2 buffer is. It has half the potassium chloride concentration, 1 molar potassium chloride. So when it's added to the solution measuring the initial pH, the ionic strength is 1 molar. So that's the only difference between these 2 buffers is the concentration of potassium chloride. The acids and bases, their concentrations are the same. And the pH that is obtained from these 2 methods are the same. So that was the reason the high salt concentration was introduced in this method. And it had a side benefit of getting a salt pH of all the benefits that were discussed a month ago when we looked at the advantages of salt pH.
All right. All right. Sounds good.
Okay, so this is the equation to calculate what the lime requirement should be in tons per acre to reach a target water pH with a Sikora 2 buffer and initial pH and 1 molar potassium chloride. It's just using algebra and the lime response curve. What's highlighted in yellow here is the relationship between water pH and potassium chloride soil pH so that we could plug in a target water pH. This method could also be used with a Sikora soil buffer pH and soil water pH, where you have the relationship here replacing the initial pH of potassium chloride with the initial pH in water, knowing what the relationship is between KCl pH and water pH. Well, much to my dismay, the formulas in the previous graph calculating lime requirement did not produce a value that we had in our recommendations tables at UK. And what I've observed is I needed a multiplicative correction factor to multiply the equation lime requirement by a correction factor to get to values in the table. And these are the equations to obtain those correction factors. And that is one thing that I wish I had more time to study. I did not do any lab incubation experiments to verify this. All I was doing was trying to get back to the values we had in our recommendation table so it could be calculated with one equation. And I did that, but I did that with those correction factors. In our current recommendation table, shows lime requirement a little bit differently here because it's based on 100% effective lime, and it's rounded to the nearest quarter of a ton per acre. But I want to get back to this correction factor. And when I created these equations and put them in our extension publication, I assumed that what we were obtaining was the lime requirement that would be typical from a calcium carbonate lab incubation. So I would say lab incubation lime requirement times the correction factor would equal some field lime requirement. And I thought we needed the correction factor to get from lab incubation to field lime requirement. Well, the data from Carl and Moore out in Oregon State has proven this to be false. They had calcium carbonate incubation study on Oregon soils, and they did the Sikora 2 method on these soils. And the graph you're seeing here is the incubation lime requirement from the calcium carbonate incubation versus the method estimated lime requirement without the correction factor. So it's based on that formula I showed earlier without the correction factor. If that formula was actually calculating the incubation lime requirement, the slope of these regressions should be 1. But you're seeing the slope being about 3. So the incubation lime requirement is about 3 times that from the method estimated lime requirement. The equation lime requirement times 3 equals lab incubation lime requirement. They also performed the single addition calcium hydroxide method, and it was very striking that they had very similar slopes of about 3. So it looks like about the same correction needed to be applied to the calcium hydroxide method for comparing the incubation lime requirement to the method estimated lime requirement. This graph is shown just showing the graphs for the calcium hydroxide and Sikora 2 method with a target pH of 6.4. And what I am overlaying on top of this are the correction factors that Georgia uses with that single calcium hydroxide method and the correction factor that we use for our method. And you see that it's very, it lies pretty much on top of the data they observed. And these correction factors do not go to higher lime requirement because these are extremely high lime requirements, greater than 5 tons per acre. And both Georgia and Kentucky pretty much top off max. The maximum lime requirement is usually just 5 tons per acre. So, I was very encouraged that this correction factor seems to be pretty consistent among a wide range of soils, the low CEC soils in Georgia, the higher ones in Kentucky, and the ones in Oregon. So, I thought if we had to introduce a correction factor, I was thinking, oh, well, we'd have to calibrate this correction factor to different type of soils. But that may not be the case. Maybe one correction factor could be used. There is an Excel calculator that I developed that we could plug in any water pH, buffer pH, target pH to determine lime requirements. I use this a lot when agents ask me to calculate lime requirement of some pH. It's different than what we have in our tables. So I guess this is my last slide that I want to end in. I want to end with emphasizing again what I think is important in this work of determining lime requirement. I think a very important parameter to be sought is the slope of this lime response curve, because once you know that, that's you have the answer. You have the parameter to calculate pH, target lime required to any target pH. It seemed it'd be suitable across a wide range of soils. So I'll end in a little bit of humor and say that I think this slope is the holy grail, the whole enchilada, and it's 42. And if you have to seen or read The Hitchhiker's Guide to the Galaxy to know what 42 is. And 42 is the answer to everything in the universe. So that is it. The publication has a list of references if you're interested in looking at it further. So with that, I'll open it up to any questions or discussions y'all may have.
Please, people, jump in. I think this was a great presentation. I find it interesting that 3 is the magic number for the correction factor, no matter whether the soils came from 3 different states. So go ahead.
I was real impressed with that. Yeah.
Hey, Frank, this is Rao from Florida.
Yeah,
Quick
Rob.
question. Is there any ionic strength issue with AE buffer that we have to deal with? If we ever working with AE, the same thing on AE?
I don't know. I didn't look at AE buffer with respect to determining a line response curve, like with the initial pH. So I didn't explore that with the AE buffer. I just looked at mimicking, creating the same buffer pH. And to tell you the truth, I'm forgetting what the ionic strength is in the AE buffer.
Yeah, that's what I was wondering too. But I know you have added KCl here, but I don't know if anything similar happens with AE too.
Hey, Frank, this is Brian Hopkins. I just wanted you to, not a question, but just a comment that Sikora is actually got a little bit better precision than SMP when we measure that across laboratories. Anyway, it came out really, that and Woodruff came out on top in terms of precision. So I thought I'd just mention that to you. Happy to share that information with you.
Oh. Yeah, thanks. I didn't know that.
Hey, Frank, I have maybe a little bit of an esoteric question. I noted on the Shoemaker incubation figure caption, the soils were incubated for 17 months and then aged for 3. What do you think the purpose of dry aging for 3 months was?
I don't know. I don't.
Seems like more than just like, a random afterthought when we got around to it.
Yeah, it could have been. Maybe that's how long it took them to get around to it, and they put it in the. I tell you, that thesis has there's a lot that is hard to really understand why they did things. But yeah, I don't have an answer, John. I'm not sure.
It's interesting.
Perhaps the student was still taking classes that semester and he had to put them on the storage until he could get to them. So, hey Frank, so I have another question. So I understand the linearity between where the aluminum takes effect in pH 7.1, 7.2. But what do you think about these really strongly acid soils? Because when I look at databases, I see a lot of soils now that are, well, not a lot, but a significant percentage of soils that fall below that, say a water pH of 5.4, which probably has aluminum in it. What do you think? What do you think about down in that area there?
Yeah, if they're really strongly acid, maybe they're still linear down here. You see some of these soils have linearity. I don't know. I guess you'd have to look at them individually to see what the response looks like in this region below 5.2 compared to above 5.2.
So correct me if I'm wrong. So if I'm dealing with a water pH of 5.4, where I see the aluminum start to be an issue, so one normal KCl pH, that's going to be probably about 4.2, 4.3.
4.4, 5.4. Yeah, it's about 1 pH unit. The lower pH is about 1 pH unit difference. As you increase pH, it's 0.9.
Okay.
At higher pH, the difference. And that's what's really confusing in this work. I mean, it's constantly, what pH am I looking at? You know, just when I'm looking at my own data, you know, is it KCl pH, water pH? It just, it gets mind-boggling sometimes trying to tease this out.
Well, we have time for one more question, and then we're going to move on to John Spargo and Sarah Lyons' presentation. Any more questions? Okay, well, this presentation's been recorded. We can go back up online. The people who are part of the group that's not here today can be more than happy to go there and view this. I think this is a nice, dovetails well with what David Hardy did, last month, talking about the pH method. So let's move on. So John, are you or Sarah, who's going to do the presentation on this? Okay, John's got his hand up. You got the forum, you got the screen sharing, we're set. You're muted, John.
Can you see my speaker notes or the presentation?
I see the presentation. I think everybody's got the same.
Okay, good. All right, thanks, Bob. So I'm going to try and keep this relatively brief. Got time for additional discussion and to keep us within the hour. Bob asked about a month ago now if we could share some results specifically about pH and buffer pH methods that we collected from this survey of land-grant universities. I think most of you have either or both heard us present summaries of the survey and or participated in the survey itself. So hopefully the stuff that I'm going to share with you today is something a little bit new. I do just want to provide a quick overview for those of you. This is the first time you've heard anything about it. We ran the survey. I think we initially sent it out in 2020. We've been collecting and correcting and dialing things in for the last couple of years. And as you'll eventually get to see, it's because this was a really comprehensive survey. We collected a ton of information and everything from general stuff about does your institution have a public soil test service lab, number of FTEs working in soil fertility calibrations through recommendations, philosophies, and terminology. And then we dialed in on soil test methods. And, obviously today we're going to really focus on pH and soil acidity, but we also collected information on some other things, whether or not, if you have a lab, if we're participating in proficiency testing, soil health, et cetera. So first, where are we collecting responses from? We had really good participation in this, and in large part, that's because we've got a lot of really good colleagues in this area, as well as the leadership. We distributed these through each of the regional coordinating committees and sort of tasked the chairs with really riding herd on this and making sure we got responses from as many states as we could. In the end, we ended up with a response from every state, 48 states plus Puerto Rico. We only ended up missing Alaska and Nevada, and no surprise, neither one of those has a soil fertility specialist to answer these. So the other thing, I just want to share this one piece with you. We were asking a lot, in addition to the types of soil fertility research and about recommendations, we were asking a lot about methods. And one of the things that we recognized is that whether a state does or doesn't have a service lab, has implications for not only how we view our recommendations, but also the view or engagement in the analytical methods themselves. So At the time of running the survey out, these are the 30 states where there currently is, a public service lab offering soil fertility testing and nutrient recommendations. Jumping right into methods. With regard to soil acidity, we did ask a number of questions about how folks were measuring pH and or buffer pH, how they were making lime recommendations. We've got some additional details, and I just want to note that we did ask about things like, do you make the measurement while you're stirring? Do you rinse in between samples? I'm not going to get into any of that here, but that's available if anybody's interested in taking the deeper dive. So first, looking at pH methods, the dominant one is clearly pH and water 1:1. We do have a handful of southern states that are using the wider ratio of 1:2, and I think there's probably pretty good explanations for that. Just a handful and 100th molar calcium chloride. And then again, at the 1:1, Vermont's method was dialed in for a 1:2, and I'm not sure what the divergence was on that one. Just an interesting note. Of course, Kentucky, the outlier, 1 molar KCl, and then a couple of the western states where they're recommending a saturated paste. So one note, just to circle back and put things in context here, we asked the question, does your laboratory, or if you don't have a laboratory, do you recommend using this method for measuring pH? Looking at buffer pH, I think I've got an accurate count of 14 different methods. Obviously, some of these we may be splitting hairs. We might be able to bend, together Malick and modified Malick, and from what we just learned in the last 30 minutes, maybe the Sikora and SMP. I did not realize how the Sikora 2 diverged from these two, and that was, I learned a lot in 30 minutes there. Thanks for that, Frank. A couple of, I think, interesting notes here. Vermont never really used a buffer to make their lime recommendations. They're actually using modified Morgan extractable aluminum to get an estimate of soil buffering capacity. And I think Frank mentioned, the method they use in Georgia with the single titration point of calcium hydroxide. Just a few more notes I think are relevant to this discussion. One of the things we also asked is, what year is the last time that the lime recommendations or procedures for making lime recommendations were revisited? And then Sarah pulled these maps together and just split it into 3 bins since 2002, so within the last 20 years, more than 20 years ago or before 2001, or currently in progress. And I was really pleased, seeing this summarized this way. 14 of the states responding, noted that they've looked at this within the last 20 years. 10, it's been more than 20. 3 currently in progress. Western states where soil acidity is starting to become an issue, and a little bit disheartening, but not calling anybody out, is that in this, these gray boxes includes 9 states that weren't sure what the provenance of their lime recommendations were. Frank mentioned, many states cap their lime recommendations at a certain threshold. That was one of the things we asked about. So these in blue have some ceiling limit, the maximum amount of lime that they would recommend being put out in one application. And it ranges everywhere from 2 tons or 4,000 pounds all the way up to 24,000. And I imagine a lot of this depends on a couple of things. One is the management systems that they're working in, crop rotations and opportunities to get in lime, whether or not continuous no-till is a large part of the management practice. And then the other one is whether or not we're including some sort of, whether we're assuming some standard grade of lime that everyone gets or specifying calcium carbonate equivalents or neutralizing value. I know specifically for Pennsylvania, this is not 10,000 pounds of calcium carbonate equivalents, that's 10,000 pounds of actual material. So if we give you a lime recommendation, say of 5,000 pounds of calcium carbonate equivalents, but you're going to work with a material that's only 50% calcium carbonate equivalents, well, then that's going to meet your cap. We're not going to recommend applying any more than that. Finally, leading into the next question, do you specify either neutralizing value or calcium carbonate equivalents with your lime recommendation? And most states do, responded that they did. There are a handful that don't. And, this kind of gets into some of the other discussions and nuance and the survey that Bob sent out late last week, and sort of trying to get a handle on what how we come up with our lime recommendations and sort of pulling the calcium carbonate equivalents out of that so that we can normalize things across recommendation systems. And finally, we asked what the typical target pH is used for field corn. Most states are coming in somewhere between 6 and 6.5. A few notable outliers: Nebraska, as long as we're over 5.2, everything's good. North Carolina for mineral soils has a target pH of 6, while for the organic soils, 5 or close to 5. But in general, between 6 and 6.5. And I'm going to quickly share a reference. If you guys haven't seen this paper, Follett and Follett from 1983, a really interesting paper published in the Journal of Agronomic Education. Just a really nice overview, sort of extension version of soil acidity, the chemistry of soil acidity. But they also did a pretty extensive survey of labs in different states, and they weren't clear whether or not it was university labs or all labs, but got a really good summary of methods used to measure pH as well as buffering capacity, and then did a really nice sort of strengths and weaknesses of each of the different approaches. A really nice paper, and I think relevant to our discussion here. I'm going to cap it off there and invite questions or comments.
So, John, I think you did an excellent job of kind of piecing together the pH methods, the buffer pH methods, but I think it's really important to see both the target pH people are going for and then what they max out the line. And I think you make a valid point that we're not talking about tons of lime, we're talking about tons of material that can go on the field. It's quite shocking. It looks like a lot of those were about 8,000, 10,000 pounds was kind of the upper limit, several at 4,000. I'd like to understand why somebody had 24,000 in there. If they have plot data to say that 24,000 where they had a very acid soil, that'd be great. But that's more of a curiosity more than anything.
So, I mean, we've got some soils that are buffeted, are that acidic, and we come up with a lime recommendation. Penciling it out, it would take 25,000 pounds of lime to hit a target pH of 6.5. But it comes back to economics and/or logistics. It just doesn't make any sense to put on more than 10,000 pounds of material in one shot. Where we end up in a real pickle is especially in now getting away from agronomic production, thinking about a right of way or mineland reclamation kind of thing, where we're not talking about managing this piece of ground over several years. We've got one opportunity to get them with a bulldozer, apply this material, get it incorporated, and get it planted. What we've worked with those folks on is if you can't separate it out over time, you got to separate it out by field operations. So, maybe we put, 5 tons down and run it in with a moldboard plow, and then you put another 5 tons in and hit it with a really aggressive set of discs and just try and get it as well incorporated as possible.
Yeah, that's one of the challenges, excuse me, that I've run into, where you get into these no-till systems and the guys, absolutely not. I do not want tillage out there. And yet, I've seen several fields where the subsoils are in the threshold of 4.9 to 5.1, and you kind of go, well, you've got some issues there developing over time, especially from long-term use of anhydrous fertilizers. So, any other questions?
I'm surprised Nebraska pH for corn is anything at 5.2 or greater. Is that due to lack of lime in Nebraska, or why such a low pH for corn in Nebraska?
Go ahead, John, if you have any insight.
Yeah, I mean, I can speculate. I think, if you look at where, aluminum doesn't start to become toxic until you hit 5.2. The real question, I think, Frank, is why are we liming all of our other soils to 6.5? Corn doesn't need it. The problem is that the soybeans or the alfalfa or, the other crops in the rotation do. And they did a bunch of work in Virginia, way late.
In North Carolina too.
Yeah,
They don't require such a high pH.
yeah, they corn yields topped out, 5.5. It's fine.
To your point, Frank, excuse me, Brian, Frank, to your point about Nebraska, there's a lot of lime sources in eastern third of Nebraska. The first 7 counties, 8 counties in from the Missouri River, there's a lot of lime deposits there. The problem is once you go beyond that, the trucking cost becomes a big issue.
I was going to mention that I used to work for Servitech, manager lab in Hastings, Nebraska, and I wondered that exact same thing. And we consulted when I worked for them. We consulted on about 1 million acres of crop ground, and what we discovered is that a lot of those subsoils, even though the surface soils are acidic, the subsoils are still fairly calcareous in a lot of the areas, even in eastern Nebraska, and so we. Frankly, oftentimes our guys were just not finding that they had to lime to a very high level. Now, in some places, though, where the subsoils were more neutral or acidic, we did find that we really did need to bump that up a little higher than that level. So, anyway, that's my opinion, is that it's flavored by that subsoil chemistry.
So, the other question I've had with those is, what do you do about the triazine herbicides? Continuous corn, pH of 5.2.
Yeah. Well, it's interesting that, and I don't disagree with you. I would say liming rates of 6.2 on corn. And the fact is, you don't want to go in there very often, so you may push it up a little bit, but whatever. Okay, well, we're coming up here. We got just a few minutes left. So we've got on my calendar here set for the next meeting on the 18th of April. So if that all works for everybody, we'll see everybody at 10 a.m. Mountain Time, noon Eastern Time on the 18th of April. We're going to have a discussion from one of our colleagues here. Just a second, I'm going to move my screen over. Luke Gettabani is going to do a presentation on the chemistry of soil acidity. And hopefully by then I'll have some data back. I have 6 respondents on that survey I sent out for coming up with the lime recs from the various states. I'm going to try and get that up on a Google Docs area so everybody can just go in there and edit that on that and take care of it rather than returning all those emails. So any other comments before we break this off?
Hey, Bob and John, I just have another comment. And it seems like, a lot of states are just kind of keeping it to 6, and if there's not a further gain in anything, why do we keep adding? Like, I think that seems like a really good point to discuss. And, we are in our state, we are thinking of revising our recommendations. Is there a real benefit to getting to 6.5? Can't you just do 6 and reduce farmers some money that they have to add the line?
We look at it as an investment, and you're also going to take care of those low spots in the field that you can't account for when you're soil sampling. There's a lot of variability, and it's an investment. You're constantly acidifying your soil with all of the nitrogen. And so, it's more about get it up to that point and then enter a maintenance level instead of having to do 4 or 5 tons a year. So from a practicality standpoint, it just makes it easier to manage.
Well,
And I think it's a relevant point that some of the legume crops love that little higher amount, right? So go ahead.
no, I guess I was saying that, so Jay's point is good, but the challenge is we keep getting rainfall. So even if you add more, it's not gonna stay there for much longer, depending on how much rain you got. So I'm not really sure where, like, I follow the logic that you have tremendous variability, but if you capture a really good soil sample that takes care of the variability, maybe you can live with a little less lime application in those fields.
Well, and I'll make one addition to what Jay said. The other thing, the applicator isn't perfect either, right?
No.
So, I don't know what the precision is on applicators for lime equipment, but I would say it's probably easy several, say 200, 300 tons the acre variability. So you got the variability in the sample, the spatial variability, and the variability applicator. We kind of put, a correction factor in for all that. So.
Kentucky, we recommend lime to get to 6.4, but we don't recommend any lime if it's above 6.2. So 6.2 is kind of the trigger to whether recommend lime or not. That should probably go down to 6, maybe. Only recommend lime if you're above, if you're below 6 or not. But right now,
we actually get recommendations for both. So our target is 6.0, but if we have growers that want to know what, if lime's cheap that year and they want to try to get it to 6.5, we also give them that rec.
Very good. Okay, well, it's top of the hour. So I guess we'll have everybody the 18th. Luke, I'll be talking to you by email about some stuff. In fact, I'll probably give you a call. So very good. Steve, you want to stop the recording and we'll go on from there. And thanks very much.